you go.
Thanks.
Thank you very much.
Forward is forward. Right. Well, my name is Les Peters. I work at Neustar, as the slide says, and I'm here to talk about a tool that I wrote for my team called Webtop. It is based off DNSTop, which was presented here at NANOG back in, I think it was number 26 or so. So here we go. So Neustar launched about a year ago a HTTP DDoS mitigation service called SiteProtect, based on our prior experience with mitigating DNS attacks. During that time, we were using DNSTop extensively to analyze different aspects of the DNS traffic. But with this HTTP traffic, we decided and realized that we needed something a little different, but we wanted the same sort of interface. We wanted to look at post and get content. We wanted to look at the source and destination IP addresses and the various HTTP headers. We wanted something easier than having TCP dump feed into a series of awks or greps or seds or Perl scripts, and every engineer doing their own thing and getting different results. So they asked me to write a tool, and that tool became Webtop. Webtop is very DNSTop-like. It was the inspiration. It can analyze and aggregate the data coming in off an Ethernet port based on hosts, based on the get and post requests, based on the source IPs or destination IPs. The user agents, which is a target or an avenue that a lot of DDoS attacks seem to have certain aspects that make those jump out at certain engineers, and thankfully we can highlight those. Also, any referrers that don't look normal for the traffic expected. Language packs as well, so that's another avenue. If we're seeing a customer in Saudi Arabia getting a lot of traffic from Canada, generally not something they expect to see. So if that jumps out, we know there's an avenue we can address the traffic. Also, for those of us, obviously a good crowd here, ASPath, and then a GeoIP data, both of which are based off of open source CSVs that could be upgraded to anything, any more precise information backends. In addition, most of the header requests we also break down within either source IP or destination IP in case there's one particular or a handful of destinations or sources that are having a certain type of traffic, we can isolate to that point as well. In addition, just measuring bits per second or packets per second is something that we can also do. In addition, but sometimes you don't want to see everything that's coming over the pipe. So I wrote in the ability, much like DNSTop, to put in a Berkeley packet filter so that you can exclude or just focus on a certain type of traffic from a certain network. But since we are dealing with HTTP traffic, I also included an HTTP filter so that we can just look at certain types of filters, certain type of HTTP traffic headers, any transactions that have this particular pattern would show up in the display and nothing else. Now, it's not just like DNSTop usually used, a live action tool. It's also usable as a post-action event, a tool. You can feed it in multiple files, and then it will produce a report based on that content that you asked for. Any of the views that the interactive tool has, the report side of the tool will also utilize. Here we have a top talkers list. And here, actually something referenced earlier at NANOG, traffic from just iPhone and iPad devices. So in the event something odd was happening in that particular area of the internet, we'd be able to focus on that. From my perspective, and hopefully from yours, it is 100% Perl code, aside from the libpcap that it utilizes through Perl modules. It's extendable, so if you know of a particular regex for an HTTP header that you want to look for, you find a particular keyboard command key to activate that view, and then some way to display the content, you can extend it as much as you'd like. And it is available on SourceForge. And thank you.
That was lightning.
That's not bad.
Yeah. Thank you very much, Les. Next up, Manish Karir with IPv6 utilization.
Good afternoon, everyone. What NANOG would be complete without at least one IPv6 talk, so I'm here filling in that slot. My name is Manish, currently with the DHS, S&T Cybersecurity Division, and no matter how many times I say that, it still sounds weird, so that's just the current organization. What I'm going to talk about today is an experiment we were working on with Jeff Houston, essentially similar to the platform that he described yesterday. It's a web-based experiment that pushes out ads that run flash code, and then you can run a variety of tests with that flash code. And in this case, the tests that were being run were IPv6 probing tests. I'll describe very at a high level what overall statistics we got, and then talk about a deep dive into what is the population mix we see in terms of IP addresses. I'm not going to talk about what was the performance of IPv6 clients or anything like that. That's the subject of a different talk. All I'm going to talk about today is the population mix. What IP addresses do we see when we're just observing them in the wild? So here's the overall volume of unique IP addresses we saw. The experiment was run for 6-month duration. Right in the middle there where you see a little bit of ramp up is IPv6 launch day. And you see clearly a huge buildup in the terms of the number of unique IP addresses we observed right around the time of IPv6 launch day. Right after that, you see a huge drop-off in the number of unique addresses we observe at our web server. Overall, after IPv6 launch day, it's actually much lower volume than it was before, even going far back as January of this year. So what's the population mix? We divided up into either native or Teredo or 6-to-4 transition technologies. And no surprise here, we see Teredo with over 80%. Teredo addresses accounting for over 80% of all IPv6 addresses we observe. Overall, we observe 14 million unique IP addresses, which according to me was a surprise. I didn't think there would be 14 million IPv6 addresses out there on the internet, but they exist. Only a very, very small fraction, 1.3% of all our addresses we observed were native v6 addresses. You see on the table there, breakdown by region. RIPE region with 90,000 addresses was twice APNIC and ARIN. So they're clearly taking the lead role in native v6 adoption. This dives a little bit deeper into the regional trends of what's going on in terms of IPv6 native address usage within each of the regions in terms of ASNs. So for ARIN, we see about 277 unique ASNs. We're using native IPv6. RIPE again is twice the number, and APNIC again at 230 or 260,000 unique ASNs. 200 unique ASNs, not 1,000. Now, digging a little deeper, so IP addresses are very interesting, right? So not only can you tell at a high level which region they're coming from just by looking at the prefix, but they encode information deeper into the address as well, particularly for Teredo. For example, with Teredo addresses, the address itself encodes the Teredo server IP address. It tells you whether a NAT was present in the path, and what the client IPv4 address was that was used. So based on this, we can go ahead and parse out the bits of IPv6 addresses and figure out where the Teredo servers were in our data set. Overall, we observe about 11 million unique IPv6 addresses that were Teredo, 258 unique Teredo servers around the world, in 171 unique ASNs in 39 countries. United States having the largest number of Teredo servers, again, about 76. Great Britain next with about 33. Now, what was interesting in this whole in our data set was that even though we see fairly large number of Teredo servers globally, the top 5 servers account for almost all of the clients. So essentially, these 5 Teredo servers are really, really critical to over 10 million of the Teredo IP addresses we see. So a huge dependency in the success of Teredo there. Digging further into the Teredo header, we know we can also get to NAT IP addresses. Once we can figure out the address of the NAT, the IPv4 address, we can figure out where it's coming from, just based on the IPv4 geolocation. So we observe about 15,000 unique IPv6 addresses that have the cone NAT flag set in the Teredo portion of the IP address. Almost half were in the APNIC region, about 5,000 in the RIPE region, and Indonesia and New Zealand Telecom were the largest contributors. The next transition technology, which also encodes information in the IPv6 address, is 624. And what we did was we once again sliced and diced. For 624 usage, there's a fixed prefix 2002, and that is followed immediately by the IPv4 address of the node that constructed that address. We observe about 2.78 million unique 624 addresses. RIPE region again was 92,000. APNIC had the vast majority of 624 IP addresses we observed, about 1.4 million of those. Indonesia was the largest country that was generating these addresses, about 500,000 of these. And the last bit of information that's also encoded in an IPv6 address is the MAC address. The last 64 bits can be used to represent an interface identifier. And in some cases, that interface identifier is generated from the MAC address. The MAC address is 48 bits. The Ethernet MAC address is 48 bits. So they do something called EUI64 expansion to convert it into 64-bit address. Now, what happens in that process is that there's a telltale tag that you can look for, FFFE, right in the middle, which will identify when that it is an EUI64 address. So what we do is we go through our 14 million addresses trying to figure out how many people are using this expansion. So surprisingly little. So what we do is we, in our data set of 14 million IPv6 addresses, we observe only 174 native IPv6 addresses. These are the only ones we would expect to have this information. Remember, this information is not going to be in Teredo, but it will be there in native v6 and 64. And what we observe is only about 6,000 or 7,000 IP addresses actually had this tag embedded in them. And so we decode this and we end up with a huge list of MAC addresses. Then we go back and take this list and correlate it against MAC vendor databases, and lo and behold, the vast majority of these turned out to be Apple devices. So in conclusion, in this experiment, we studied what IP addresses do you observe in the wild, and then we go ahead and decode what information we can just from the structure of the IPv6 address. We observe about 14 million unique addresses, mostly transition technology. So apparently that is a success. Transition technologies are working. Just hope we can see greater native v6 usage pickup. And of course, in terms of regional trends, we observe higher Teredo usage in the RIPE region and higher, much greater 624 usage from the APNIC region. We're not seeing as many hosts as we would have expected, host identifiers, MAC identifiers in these addresses as we would have expected. And if anybody in the audience has any ideas of why we're not seeing those, that would be very helpful. That's about it.
Any questions?
Forgive me if I missed it, but where do you get all the addresses from?
These addresses were collected at a web server. So remember, the experiment is essentially pushing out ads, which then try to probe back to a web server.
Okay.
So we collect these addresses at the web server.
Okay, I missed it. I have an idea why you see not so many IUE64 addresses. Most clients nowadays do by default the privacy extensions. Apple did not do that until the last, until mountain lion or something. Lion. Before lion.
Yeah. I suspect since we have those HTTP logs, we should be able to go back and figure out the user agent, and from then figure out whether that's actually the case.
Randy Bush, IJ.
Oh, right there.
I would note that I don't really consider Teredo or 6-to-4 transition mechanisms. They're V4 desperately clinging to end-of-life mechanisms.
Agreed. But in terms of when we were just trying to figure out how many people could access V6, they count. So, thanks. Right here in the middle.
Owen DeLong, Hurricane Electric. I will point out also that FFFE only appears in EUI 64 addresses that are derived from EUI 48 addresses. It is possible to have an EUI 64 address that is native EUI 64, such as on FireWire interfaces or certain other media where you won't have FFFE in the middle.
Thanks. That's a good point.
Yeah, Nacho Sarikaya from Huawei. I just wanted to ask, I would like you to clarify what do you mean by that point, not seeing very many host identifiers with MAC addresses. Where do you see the host identifier?
So basically, this is the same point that I was pointing out. We see a very small fraction of addresses that have MAC addresses embedded in the host portion of the IPv6 address.
Oh, you mean the
Towards the
interface
end.
ID, IID? Okay.
Yes.
Oh, okay. Thank you.
We're going to have to cut it off to just the three folks standing right now. Thanks.
Jeff, we have
I think in the back was here first.
Yeah, thanks. Lee Howard, Time Warner Cable. I'm surprised, maybe I don't understand, the number that you show for native IPv4 clients, or maybe it was total IPv4 hosts in the Erin region was something like 41,000. I know that I have more than 41,000 IPv6 users on my network, and that doesn't include AT&T and Comcast and Verizon Wireless. So what are we missing?
Can I? Okay. So it's quite possible that the experiment didn't reach them. Remember, the way the experiment is distributed is over an ad platform. They have to be visiting some website where this ad gets pushed to them, which then can run a probe. So this represents really a sample. It's not a census. It's not going to give you the whole data set, but it's a sample.
Thanks.
Jeff Houston, APNIC. I can actually explain that, Lee, a little bit more. We're cheap bastards. So we actually bid for clicks as low as we possibly could in Google's ad engine. So our ad gets displayed heaps in Indonesia and Poland and other places. But over here, where Google thinks you're all rich, whether you are or not, it's irrelevant, our ad doesn't get displayed as much. So yes, it's a certain amount of just demographics of the ad machinery. The other thing you should also be interested in at some point is the failure rate of what actually goes on. Because we can actually see connection failures. V4 is actually working pretty well across most of the net. You know, the failure rate is well below 1% of folk who try to connect. But in V6, even in unicast native mode, the failure rate is in excess of 3%. So however we're going with V6, we're still encountering a huge amount of problems inside the network. I can see the SYNs coming in, but when I respond with the SYN-ACK, it doesn't elicit any further, it just stalls. So even though you're seeing a certain amount of uptake in V6, the quality of the V6 network is still leaving a bit to be desired.
Just one last point. So there's a lot more digging right behind that question, and you know, it's basically the last point in the conclusion slide. And I think there's going to be, you know, follow-on presentations on that. Thank you. Oh, one more. All right.
Michael Sinatra, ESN. One thing about the FFFE again is that there are platforms out there that compress ACLs because they only have 128-bit wide ACL TCAM space. So you have to compress the FFFE out of an EUI 64 address and use that 16 bits for the port number. And as a result, there are people who address statically servers that look like they have EUI 64 addresses to make the router think it can compress that address and use the bits for the port so they can have more rich ACLs. So there are going to be some weird skewing things. I don't think it's going to skew your results too much, but there are all kinds of weird things going on in EUI 64 land, so your mileage may vary.
Yep. Thanks.
Thanks, Manish. Can I have Chris Grundemann of CableLabs come up? He is going to answer the question that's burning all of our minds. What the F is SDN? Get ready, write this down. Yeah, so I decided that we were a little short on buzzwords this nanog and submitted this lightning talk. So what is SDN? What's software-defined networking? Any questions? Actually, I think the best way to define a new buzzword is with an older buzzword. So it's cloud routing, perhaps. I think the best way to look at this is to start with some examples, right? And obviously, the first one, what's caused the most recent hype is OpenFlow, which is basically an interface between controllers and switches, right? It's just a way to program switches. It's entering fib entries into a switch from a controller that can then be centralized, put into a cloud, or what have you. And the purposes there, I think, are fourfold, right? So the one that gets touted most often, or at least first, seems to be this idea of commodity switching hardware. The problem with that argument is that you still need really high power or really high performance switching hardware. You just don't have to buy it with the software necessarily. And you still need really great switching software. You just don't have to buy it with the hardware necessarily. So I don't know that your CapEx, if you're really going to see CapEx changes with an OpenFlow network necessarily. One of the cooler pieces, though, is interfacing directly with applications, right? So now the network can be talked to potentially. These applications can interface with the controller, which can then interface with the network, and you can have perhaps network paths built and torn down by applications as needed. Provisioning systems might become much simpler. Network troubleshooting perhaps becomes much simpler if you're tied directly in. And then the next point is even cooler, I think, is that maybe you get to be able to not have to wait for your vendor of choice, your hardware vendor of choice, to add a feature for you. Instead of putting it on a list, you get to just write it yourself or have a third-party app developer write it, potentially. And then you get a global view of the entire network. Because this controller now sits off of the switch instead of having this distributed control plane that's a little bit in every single switch or router, you have one big one that can see everything, which leads to efficiencies. That's what we've seen with the big deployment at Google. Obviously, the press releases I've seen say that they're using close to 100% network utilization on these links now because they're able to see the big picture and interface with the applications directly. A newer idea besides OpenFlow is IRS, the interface to the routing system. The problem statement was just written right at the end of July, so this is fairly fresh, and then there's a framework as well. And so you can think of this, the first step is it's OpenFlow but with routers instead of switches. It's more different than that. It's instead of removing the control plane, you're just interfacing with the control plane. So you can still have this off-board controller potentially, but then it's interfacing with the existing routing protocols. So you can inject things into existing routing protocols and get information out, which I think is another big part of SDN, right, is getting more and better information out. How do you actually measure users' quality of experience in real time on a service basis rather than just counting bits going across an interface? SDNP, Software-Driven Network Protocol, is another example. This is a framework that was built around a BOF at the IETF. The draft that they wrote has now expired. But I think the framework that it defines is very useful for looking at kind of the evolution of SDN as we go forward. It basically has this kind of 4-box policy off to the left, and then kind of 3, you have your applications, and then network controllers or orchestrators, and then network devices, and the communication path between them, right? I added this in here. I have actually no idea what it is, but it's being announced today in Darmstadt, so I thought I'd throw it in. Network functions virtualization. There's a bunch of big telcos have gotten together and they're announcing this today. So we'll see what comes of that. As kind of a look into carrier SDN, right? So moving it out of the data center into the carrier space and into the ISP space, which is why I'm interested in SDN, is that idea of moving it into ISP networks as well instead of just data centers. I know ATIS is also looking into defining risks and rewards of SDN and that kind of thing. This is one that many of you probably have not heard of, Active Virtual Network Management Protocol. This came out of a PhD at GE, and is looking at, so active networks are basically, there's executable code in the packets going across the network that are affecting changes along the way, right? So your packets are actually instructing the network as they travel along it. And then with this virtual network management protocol, you're actually proactively, based on potential future events, doing network management instead of reacting to things, you know that they're going to happen ahead of time and can manage them kind of in a time warp. And there's more and more, right? So SNMP really is the first one that came about, which started right about the same time that IP started, very closely after. It was designed for humans to interact with the network, not applications, but it's a software protocol that's used to manage networks, right? So SDN, I think. NetConf, obviously, Forces is another one that hasn't really gone anywhere, but does that control plane separation as well. PCE is an idea to build MPLS LSPs off of LSRs. So you have another device, a path computation element that you add into the network that then can build LSPs and send out labels and things rather than the ingress LSR doing it. CDNI is another one that's looking at sharing information between CDN providers. And then obviously down to that Perl or shell script you've written to configure your network or pull information out of your network, right? It's software defining the network. And also, I don't necessarily like the define term, right? Because it's two ways. We're really talking about two ways. We want to put information into the network, but we also want to get information out of the network. So I don't know that SDN is really the best term, but we've been doing it for a long time, right? So I think I can more easily tell you what SDN is not than what it is. It's not OpenFlow. It's bigger than that. It's not just one protocol, right? And it's not really new. So SNMP, again, has been around for about 24 years. So we've been doing this for a long time. We're on this kind of continuum of abstracting network things out with software. So if we look at yesterday's SDN or even today's SDN, really we call it BSS OSS instead, right? So you have your ordering system talks to your provisioning system, or a person gets up and moves an order to a provisioning system. And then the provisioning system then can either provision services or tell someone to provision services into the network, right? So that's kind of the way it looks. The OpenFlow model is to kind of replace that, do this network control layer that's OpenFlow. All the applications talk to OpenFlow, OpenFlow talks to all these switches, and that's it. Possibly great if you're building a greenfield data center, maybe not as practical in other cases. So I see more of an emerging ecosystem around SDN where there's a number of APIs needed here, right? So you've got those applications up at the top, which then can talk to some kind of global orchestrator that collects all the information from the applications and is able to understand what the applications are asking for, and then push that down to something like an OpenFlow controller or an IRS controller or an NMS, EMS, whatever else you're running in that kind of network control layer, which isn't necessarily on the device. And then those, of course, then talk to your actual switches and routers in the network. So what is SDN? I think it's the current name for a continuing trend towards greater network virtualization through software abstraction. It's not new, and it's not necessarily well defined yet, but I think it is exciting as we extrapolate this out into the future and you look at what it means for networks. Lowering OpEx through greater efficiency and potentially really customizing networks on the fly to what they're intended to be doing is interesting. Another thing to think about, I think, is if SDN really is the third epoch of networking, as some have claimed, what do we want that to look like? Do we still need packets, or are bit pipes a more efficient method of moving large amounts of data? And with that, I think I've left about a minute and a half for you to throw fruit. No questions? All right. Thank you.
Thanks, Chris. That was great. A couple quick announcements. Members, please take the time to vote in the analog elections. Non-members, go join so you can vote. Attendees, all attendees, please fill out the surveys. We still have some giveaways, I believe. And we're heading out to the break now out here in the foyer, sponsored by Cyan and Infoblocks. And after that, we'll have the peering track upstairs in the Houston Ballroom, hosted by VJ Gill. Thank you very much, everyone.